All right, welcome back, everybody. So last time we talked about the modeling cycle of applied math in general. Really, this is we discussed how we go about creating a mathematical model to describe some physical phenomenon. And I'd like to take this video to illustrate that process with a fairly simple example. So let's go ahead and take a look at this example in the notes, example 2.4. We're going to go ahead and suppose that we are we're control engineers at a cheese factory, and specifically what we're doing here in the cheese manufacturing process, there is usually some brining process where you take your blocks of cheese and you in effect season them with a little bit of salt. So what we're going to do here is we are going to suppose that we are charged with trying to monitor this brine content. So wherever the cheese is being dumped into, whenever this cheese is being dumped into the tank here, we're seasoning it. We need to know exactly how much cheese is or how much salt is in that tank. So let's go ahead and figure out what's going on here. Let's say that there is a 1,000-gallon tank. Right, and that's not saying that that's how much water is in the tank, because I'm going to go ahead and tell you that there are 900 gallons of water in the tank at the moment. So once and of course I need to tell you how much salt is in the tank. Well, as it turns out, we're going to go ahead and suppose there is no salt to begin with. So no NaCl at start. Right, and that would be this line saying that we have pure water. 900 gallons of pure water in the tank. So what you would do as a control engineer, you would probably have some sort of input tank or input source that has a certain amount of salt in it. And this is, I'm going to tell you, there is 1/10 of a pound of salt per gallon of water that's coming into the tank. And this is happening at a rate of how fast? How fast are we pumping this guy in? At R gallons per minute. So at R gallons per minute. Okay, so there's just a whole bunch of brined water coming into our tank here. And let's see, and then we also had to tell you how much is leaving the tank. So you want to be able to monitor how much is coming in and weigh that against what is coming out. So this is also, for simplicity, this is going to be coming out at R gallons per minute. Okay, so notice I was able to tell you how much salt was coming into the tank, but there is going to be a variable amount of salt leaving the tank, which is why I can't tell you how much is going to be leaving the tank unless I start naming some variables here. So this is going to be part one of our analysis in constructing a model. We have to come up with some mathematical description of of how much salt is in this tank. Now, there are two ways that we could do this for this particular example. One, we could be talking about, we could find a concentration. Concentration of salt at a given time. Or we could talk about the weight of salt at any given time. And you know what, to figure out the concentration, you would have to know how much weight of salt there is anyway. So let's go ahead and just try to find an expression for how much salt we have in pounds, right? Since we already have pounds up here as a measurement, we can go ahead and try to solve for how much weight of salt there is. And let's go ahead and call that W of t. So this will be pounds of salt in tank at time t. And since we're going to go ahead and start measuring after a certain point in time, we can go ahead and say that we're starting at time 0. We can just make this arbitrary assignment of where the start time is. All right, so that means that we have up here, there are W of t pounds of salt. Okay, now, how much salt is actually leaving the tank? Let's actually think about this one. Well, the total amount of salt, yes, it's going to be given as there should be some weight involved here, but if we look at the top, we want to be able to use a concentration because that actually cancels really nicely with the flow rate R, right? Specifically what's happening here. So notice that, let's see, 1/10 of a pound of salt per minute times R gallons per minute. Do I want times? No, I don't want times. I actually want a division. And in fact, what I should be doing in order to get gallons per minute or pounds per minute or pounds per gallon, let's see, how fast do we want to make this happen? Well, this will be, yeah, oh no, that was right. That was totally right. I just misread my work. So 1/10 of a pound of salt per minute, or per gallon, not minute. That's where I messed up last time. There we go. Per gallon times R gallons per minute. So this is an honest to goodness product, right? And the whole reason why I'm doing this is so I can cancel out the gallon units and I'll wind up with R/10 pounds per minute. Okay, so this is the whole reason why we want to get things in terms of, get our flow rates at the entrance and exit here. We want to get those guys in terms of concentrations rather than weights. So I need to know what's the concentration, so this will be in pounds of salt per gallon. Well, how much salt is there in the tank per how much weight, how much volume is in that tank? Well, we know how much weight there is. There's going to be W of T pounds, but what's the volume? What is the volume of water in this tank at any given time? Well, let's set this up. For volume, which very well could be changing over time, for V of T equals gallons, and this is of brine, right? Gallons of brine solution. It could have salt in it. It could be pure water. Who knows? So we do know, based on this very simple law here, that dV dt, how much the water content changes is based on how much comes in, and we take away how much is leaving. Right? This is a simple manifestation of conservation of mass. Right? So again, this is a physical law that we are expressing as a differential equation. Now, how much water is coming in? Well, have a look. There's exactly R gallons per minute coming in. That's a flow rate, so we should use that. And it's also leaving at the same rate. So that means I have R gallons per minute minus R gallons per minute. So that means that my volume is not changing over time. dV dt is 0, which would imply V of T is a constant, V0. Now, what is V0? Well, it's how much water I started with at the beginning of the problem, and that's the 900 gallons of pure water that are in the tank, this stuff in blue right here. Excellent. Great. Wonderful. Spectacular. So that means that if I come back up here, I know exactly how much volume is in my tank. It's a fixed 900 gallons, right? And I'll just go ahead and highlight that in red on the right and the units as well. So with this same paradigm in mind, let's go ahead and set up the differential equation modeling the weight. So this is weight of salt at time t. We're going to go ahead and set up W dW dt, and this is once again going to be a conservation of mass, the rate in minus the rate out. Now, bear in mind, the units here, this is going to be in pounds per minute. Okay, it's going to be a weight per time, right, based on what the units of W are and the units of T are. So be very careful when you're looking at this plethora of numbers here, trying to figure out which numbers go where. You should be able to go ahead and use this little trick of dimensional analysis to figure out if you're using the right numbers at the right time. So I always advocate that you keep track of your units. So the rate in here, it was 1/10 of a pound per gallon of salt times R gallons per minute. And we're going to go ahead and subtract off rate out. I just realized I didn't put that in there. Subtract off the rate out, and this is going to be W over 900 times R gallons per minute. And let me go ahead and bring that down to the next line, just to make it a little simpler to read. Subtract off W over 900, and that'll be pounds per gallon, times R, and that'll be gallons per minute as well. And let's go ahead and simplify this a little bit and then drop our unit notation. R over 900 W, dW dt. Phew. And we need to make sure we have an initial condition in here. Well, if we were starting off with pure water, you ask yourself how much salt is in pure water. Okay, remember, distilled water, none of this bottled water garbage. So we have 0 pounds of salt to begin with in the water in our brine solution. And this is the mathematical model that we need to set up, right? So no problem there. We actually have exactly what we need as far as a mathematical model is concerned. So that's really step one of our modeling process, is to come up with some expression that we can play with mathematically. And this is a simplistic model that's not really taking into account too much beyond a cursory glance at the system. We'll discuss how this differs from reality in a moment, but that, if I were to number this, yeah, I'd go ahead and say that this is part 1 of our modeling process. So we come down to part 2, where we actually solve the model. And we can go ahead and do this very quickly. dW dt plus R over 900 W is equal to R over 10. This is in the form of a first-order linear equation, which we know how to solve with integrating factors. So this is d dt of e to the R over 900 t times W, which is equal to R over 10 times e to the RT over 900. I can integrate both sides with respect to t and wind up with e to the RT over 900 times W, and that is equal to, if I'm careful with my division here, this will be 9 e to the RT over 900 plus an integrating constant, and I go ahead and divide through by this e to the RT. Is that 9? No, it's 90. Yeah, 90. Plus c e to the minus RT over 900, not 960, that is a 900. There we go. And that would solve the differential equation in general form, but I use my initial condition to show that 0 equals 90 plus c e to the 0, so c is equal to minus 90. And my final particular solution here, this is 90 times 1 minus e to the minus RT over 900. And that is the complete solution to this model, provided t is greater than or equal to 0 as per our initial condition, right? We weren't studying the model before we were looking at it, so let's assume that we were looking at it starting at time 0. That goes ahead and solves the equation thusly. All right, excellent. So there's a couple of things that we can notice about this. First of all, we are done with the analysis here, or are we? No. So preliminary observations. This would probably still fall under the second step of the modeling process. So preliminary observation 1, there's a limit here as time goes off to infinity. So the limit of this is going to be exactly, weird how English works in different ways there, 1 minus e to the RT over 900. Because r is a positive number, right? It is a rate flowing into the machine, not out of it. We actually wind up with a decaying exponential here, e to the minus RT. That's right, okay? As t goes off to infinity, we wind up with 90 pounds of salt. So notice that's not the concentration in the tank, not the limiting concentration. The limiting concentration which is probably something that we want to monitor as control engineers, the limiting concentration. This is going to be W of t, or the limit as t goes to infinity of how much salt is in the tank divided by the volume, but the volume is constant over time, so this will be 90 pounds per 900 gallons, and we notice, hey, 1/10 of a pound per gallon. That was exactly, if I scroll back up here, that's exactly what this number was at the outset, right? So what we really get from paying attention to this model and solving this model is kind of what intuition would tell you, is that if you left this thing running for a long time, then the concentration of the brine in the tank should equal what you are putting into it, right? If there's only one source and one exit, they're flowing at the same rate. You're not taking any other salt out of the system. You're just putting in this constant concentration. Then yeah, you should expect your model, you should expect your brine to reach that concentration, or at least get close to it over time. Okay. Other observations. Well, no, we'll do that in the next step. So let's go ahead and start calling out the next step. This is our comparison against reality. Is this correct? Is this something that matches our intuition? So let's see. My statement here, we have to be humble about our almighty model of all things brine. We made a few assumptions, so let's acknowledge what they were. First, you're assuming that there's instantaneous mixing in this model, right? I didn't say so at the beginning because I wanted to make sure we understood that the equation came from a model, or it came from certain assumptions. So let's talk about the assumptions. That the minute that the salt hits the top of the tank here, we are assuming that it immediately distributes throughout the entire tank, which may not be too great of an assumption, but it's not too bad if you've been leaving the machine on for a while and it's been mixing for a good amount of time. But the point is that salt up here takes time to travel to the exit, or to be incorporated into the rest of the solution. So that's something that we haven't accounted for yet, and would actually be better suited for a model in partial differential equations, where we have to take our spatial variables into consideration as well. So one, definitely need to assume that, that we did assume that mixing was instantaneous. Second, recall, so we didn't say so at the outset, but assume that the salt was not lost out of the tank. So in other words, these are the only two inputs, right? The only input and the only output in the tank. What about evaporation? What about supersaturation? What about crystallization on the sides of the tank if you've been supersaturating it? There are physical limits to what you can add to the tank here. So let me keep that up there and then just keep scrolling. Right, so the idea is that there are going to be certain aspects of the scenario that you don't know about, and that's the whole reason that we're studying them. We are proposing a mechanism by which we believe this system works. We are taking that assumption, or that basic mechanism, and comparing it against our physical results, our physical empirical data, and checking to see, do these things agree? If they don't, odds are either A, you've made a mistake in your model, which is entirely likely considering we are studying it because we don't know anything about it, or B, that you have neglected some important mechanism in the model, that there is something important that you have not captured. Okay, so this is in effect how the modeling cycle works. We are going to take that comparison and feed it back into the model. We're going to feed it back into what we know, and usually that means that we're going to have to tweak our equation up here. We're going to tweak our initial value problem so that this guy accounts for what we want it to account for. Again, nature does not follow the math. The math is there to explain the nature. right? And we don't know all of the nature, which is exactly why we're trying to model it. We're trying to figure out what made this system work the way it does. So let's go ahead and call that quits for this video. Let's see. The next section, we're going to be talking a little bit more about the pure side of things, right? So we're playing to this balance between applied math and pure math, and trying to say that there is something that we need to account for, and in the differences between linear and nonlinear differential equations, which we would really like to be able to solve, considering many important models are based on nonlinear dynamics.